Right, welcome to Math 150, Section 1, 2021, Lecture 5, I believe. It's always annoying that the first week has only one day, it throws us off like that. All right, so what I want to do today is talk a little bit about, spherical coordinates, a little bit about level sets, and then use the rest of the time to talk about things from the homework or just to review material. So we are basically finishing chapter 11. What does that mean? It is a time for you to have an opportunity to show me what you've learned. Isn't that wonderful? I know you've all been waiting for this. For some of you, this will be your first math exam in college. It's such a wonderful moment. The difference is, unlike other classes, if you don't do well on this exam, it's entirely diagnostic if you want it to be. I will drop your lowest exam. There are practice exams online so you can see what it is. The goal is not to surprise you. The goal is for you to be able to show that you've learned how to do certain skills. You need to be able to do them in a reasonable amount of time, and it will be closed book. Okay, so the first thing is I want to talk a little bit about the extra credit problem. So, we want to look at the numbers 1 and 2 n squared in an n by n matrix. This is a wonderful example of how to build intuition, how to attack a problem, and how to be misled. What's the easiest n to study? Nope. What is it? 1. So we start off with a 1 by 1 matrix. The determinant is 1. Building on this remarkable success, we now look at the 2 by 2 case, 1, 2, 3, 4. When we calculate the determinant, it's going to be 1 times 4 minus 2 times 3, which is 1. Minus 2. Do you notice a pattern? 1, negative 2, what do you think comes next? 3, and after 3 comes minus 4. Or maybe instead of 3, maybe the next thing is 4. Maybe it's powers of 2 with an alternator. There is nowhere near enough data to try to conjecture from this. What should we do? Yeah, look at the 3 by 3. We would have 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we do 1, 4, 7, 2, 5, 8. And when we multiply through like this, those with a negative sign, these with a positive sign, we get the determinant is 0. In this class, we're not going to really calculate higher determinants. There's expansion by minus. Some of you might have seen that in high school. You might have seen Kramer's rule. But so here's n determinant of our n by n matrix. 1, 2, 3, 4, 5, 1, negative 2, 0, 0, 0. So when you start to see this as your data, what do you conjecture the answer is? One, negative 2, 0, 0, 0, 0, 0, 0, 0, 0, 0. Yeah, so conjecture, if n is greater than 2, the determinant is 0. Okay, how would we prove this? Well, given that I really am not expecting you to be expanding things by minors, there has to be a good way to interpret this. So we've talked about the determinant has a geometric meaning. What is the geometric meaning of the determinant of a 2 by 2 matrix? So for the 2 by 2 matrix, it's the area of the parallelogram spanned by 2 vectors. In a 3 by 3 matrix, it's the area of the parallel pipehead spanned by 3 vectors. And so on and so on and so on as you have more and more things. What would it mean if the area is 0? The lines are parallel. So clearly, 1, 2 is not parallel to 3, 4. They're in different directions. What would it mean if the three-dimensional determinant is 0? So if the two-dimensional determinant is 0, then the two vectors do not give us a parallelogram, they give us a line. What would be the case in 3 dimensions if we have 0 volume? There'd be a plane. There'd be a plane. So it must be the case that if n equals 3, the 3 vectors all lie in the same plane. That means one vector is a combination of the other two. 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you see any way to get one of the 3 rows using the other 2? Let's look at the first component. We have 1, 4, and 7. How could we get 4 maybe from the first and the third? There's more than one word. Any thoughts about how we might be able to get? You've got 1, 4, 7. Do you notice anything about those numbers? They increase by 3. So you could view 4 as what of 1 and 7? They all increase by 3. So how could you relate 4 to 1 and 7? It's the what operation can you do to 1 and 7 and get 4 from it? Adding to average, you take the average. 4 is the average of 1 and 7. What about 5? Is it the average of 2 and 8? What about 6? Is it the average of 3 and 9? Yes. So the second row is just the average of the first and the third. Well, if that's the case, it's not going to give me 3 different directions. I only get 2 directions, the volume is going to be 0. If we had a larger matrix, instead of increasing by 3, what do you think we would increase by if we had a 4 by 4 matrix? 4, if we had a 5 by 5 matrix. 5. And so, hopefully this is enough now for you to figure out how to put in the rest of the details for an n by n to show that the second row is the average of the first and the third. Now let's revisit the 2 by 2 case. Why don't we get 0 there? Well, we don't have 3 things to take the average of. We need to have 2 things to take the average, and that's the third thing. In the 2 by 2 case, it's too small. One of the reasons I love this problem is that the initial behavior is very different from the limiting behavior. And this is a little bit of a theme as you go further in mathematics, that often as the dimension increases, new behavior emerges. We will see this tremendously when we get to differentiation. It is really not a big deal to be differentiable in one variable. There's only 2 paths you can take. If you want to approach a point, you come from the left or you come from the right. In the video, did Taylor talk about squiggles? And so, the secret to multivariable calculus is being able to take squiggly paths like this, converging on a point. You have to show something about limits along paths like this. This is very different than one variable calculus when you have x plus h, where h is a real number tending to 0. So it's much harder to be differentiable in several variables. And so there will be some differences as we move from 1 dimension to 2 dimensions. And I love this problem because it highlights stuff like that. Okay. Anything else about this problem? Okay. So there is a reason today is Munchkin Day. And it is not about the anniversary of the Wizard of Oz being released. It is we're talking about spheres. So this way everybody has a couple of spheres at their disposal. You must of course keep them in the sphere packaging. But we want to talk about coordinate systems. The physicists and the mathematicians choose different coordinates. It's unfortunate. In polar, we have a circle, we have a radius r and an angle theta. So it's x is r cosine theta, y is r sine theta, or r is the square root of x squared plus y squared, and theta is arctangent of y over x. So the idea is if I give you something in x and y coordinates, I can convert to r and theta. If I give you something in r and theta, I can convert to x and y. Do you think this is always well defined? That given a point in x, y, there's a unique r and theta. Given a point in r and theta, there's a unique x and y. What are your thoughts? So what's the problem point? Where is there a point where I don't necessarily have a unique point that goes to it? So it seems like the origin. So if I take 0, 0 in xy space, what is it in r theta space? What does the radius have to be? And the angle is completely free. So it breaks down at one point. At one point only, you have infinitely many choices of how to write the point in r theta. Everything else is well defined. It turns out this is not a big deal. It's not so bad. It's a little bit off at one point. It's not ideal. It's not terrible. Everywhere else, it's unique. Now, I think we all agree that overall, my drawing of circles and spheres sucks. Yeah, that's the kind. What shape do you think I'm competent to draw? Oh, long pause. I'm sorry? Okay, triangle. I think I can do a triangle. That's a pretty good triangle. What else do you think I can draw? Square. Can I do a little bit better than a square, just a square?
Square.
Oh, thank you. Right? Because a square, all the sides have to be the same. A rectangle, I can at least have different sides. The reason this is so useful is in polar coordinates. What is the equation of a circle? Well, in Cartesian coordinates, it's x squared plus y squared plus some capital R squared. That's the equation of a circle of radius capital R. In polar coordinates, it just becomes R is less equal to big R. And what does that look like? Well, if we plot it, and I put, say, theta down here and R over here, that's what my circle looks like. It looks like a rectangle of height capital R and length 2 pi. A lot of multi-variable calculus comes down to where do you want to integrate? And you have a choice. You can integrate over the Cartesian space, or you can change coordinates to another space. Which is a nicer region to integrate over, a circle or a rectangle? I'd much rather integrate over a rectangle. You can almost view this as an iteration of two integrals in one variable calculus. I let theta go from 0 to 2 pi. I let r go from 0 to capital R. I have two standard integrals. If I try to do things here, if I try to integrate for a given value of y, oh Lord, x is going, the range of x is going to depend on y. You fix y, x goes from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And so now my bounds of integration depend on one of the variables. We'll find ways to do that, but it's frequently better to shift to a nicer system where the integration is going to be easy. Now the problem is when you do that, it often changes the function. Because now rather than writing the function in terms of x and y, we write the function in terms of r and theta. Frequently, however, you will have a nice function to integrate. All right, so now this is polar coordinates. You now want to do spherical coordinates. So we use rho, theta, and phi. And the big question is, what are the ranges of everything? Well, the rho is the easiest. Rho goes from 0 to whatever the radius is. That's not a big problem. The difficulty is theta and phi. And so here's x, here's y, here's z. We are a math department, so we have the angle phi coming down. When I was young, I took physics and math at the same time. We hit spherical coordinates in physics first. They have it as theta coming down from the z-axis. Does it make a difference? No. But the formulas will be slightly different, and you always want to check and see what book are you using. So we have phi as the angle coming down from the z-axis. So if you think about what's going on, as we come down from the z-axis, we start up here, and we come down, we come down, we come down, we come down. Then I think in the video, I actually start twisting my arm back like this into excruciating pain. Right? But we still have another variable. After phi, what variable do we have? We have theta. And so once we come down here, we come down, so these longitude and latitudes, we come down to here. And now going in a circle above the equator. And that's the latitude. So we can now come down here, and then go in a circle above the equator. We're going to be a fixed height above the equator. And as my angle theta goes from 0 to pi, I go all the way around the circle. Do I need phi to go all the way back to the North Pole? How far do I need it to go? How far? So how far do I want phi to go? When should I stop? Stop where? So it's 180 this way?
Yeah.
Okay. So that gets me to the South Pole. So 180 degrees for pi radius. You can think of things in degrees if you want, but whenever you do differentiation of trig functions or integration of trig functions, you want to use radians. And the reason is, what's the derivative of sine? Derivative of sine of x is cosine of x, only in radians. If you work it in degrees, you have a factor of pi over 180. And we'll talk about that at some point. This is why we like radians. So if phi goes from 0 to pi, and theta goes from 0 to 2 pi, I come down anywhere and then I spin all the way around, I will get every point on the sphere once and only once. And that's why these are the ranges. Okay? We will have problems, of course, with one point. What is the one point where we will have problems? The origin. So if capital R equals 0, we're in trouble. Right? As long as capital R is not 0, we'll be fine, so we still have that issue. All right, the next thing is to figure out how to do things. So do you see that we have a circle above the equator circle? When you see a circle, what coordinate system do you think of? Polar. And there's a reason I have deliberately not erased it yet. What are the variables for polar? There are and theta. This is why the mathematicians use phi coming down here. They try to reserve theta for how much you're spinning in the xy plane, or parallel to the xy plane. And this is why they've introduced rho for the radius coming from the Greek r, because that way they can reserve little r to the radius in here. So if I just look at that smaller circle, it's going to have some radius, I'll have some angle theta here, and so I can represent the point here as it's going to be cosine theta, sine theta, and then whatever my z coordinates. So is everybody comfortable with using that to represent my point? I just have a circle above the xy plane, above the great equator. Its radius is going to be little r. The amount I spin around is going to be theta. So the first part is just standard polar, and the z is just reminding us we're at a height of z. All right, so we just have to figure out what is that radius. And so if you look at the circle like this, here's phi, here is rho. What would this length be over here as well? It would also be rho. If I want to find this radius here, r, I have a triangle with hypotenuse rho. What would the length of r be? That's familiar trigger. Is this the adjacent side to the angle or the opposite side to the angle? Opposite. So do we use sine, do we use cosine? Sine. So the sine of phi is r over rho. So r is rho sine phi. And so that will lead us to our final answer. X is going to be rho sine phi cosine theta. Y is going to be rho sine phi sine theta. And z is going to be this length. What is that length going to be? So this was rho sine phi. This will be rho cosine phi. We now use the adjacent side. The cosine of phi is adjacent over hypotenuse. So you would get cosine of phi is z over rho. So z is rho cosine. And that's spherical coordinates. So among the things that you just need to memorize, you need to memorize these transformations. Most of the time, we will study functions that only depend on the distance from the origin. They won't depend on theta, they won't depend on phi. All points that are the same distance away will feel the same thing. Can everybody give me an example of something in life that only depends on your distance from the object? Gravity. I was about to throw something, right? So gravity is a 1 over r squared force, at least classically, and the Newtonian version of gravity is the distance is what matters. It doesn't matter about orientation. All that matters is how far apart are two objects, and the force is proportional to 1 over the radius squared. There's a nice geometric meaning behind that. In terms of the radius, what is the volume of the sphere? Anybody know the formula for the volume of a sphere? It is 4/3 pi r cubed. If you didn't remember it was 4/3 pi, could you at least tell me it depends on the radius cubed? What should the units of volume be? Meters cubed, feet cubed, furlongs cubed, some units cubed. So if I triple the radius, the volume should go by a factor of 27. If I double, it should go by a factor of 8. So the volume is 4/3 pi r cubed. Anybody remember the formula for the surface area of the sphere? If you can't give me the formula, can you at least tell me how it depends on the radius? Proportional to r squared. And it's actually 4 pi r squared. What's the area of a circle? Pi r squared. And then what is the perimeter of a circle? Do you notice any connections between these formulas? So if you integrate the perimeter, you get the area. If you take the derivative of the area, you get the perimeter. Does that hold over here? Yes, it does. What this means is if you can remember half of your formulas, you can literally derive the other half. And if you want to think about why that's true, if I take a sphere of radius r and I increase it by a small amount, you could look and see how the volume changes. And the volume change is essentially going to be the surface area times delta r. And so if you play a game with that, and I encourage you to try to do that, you can actually see that it's going to come in as the surface area has to be 4 pi r squared if the volume is 4/3 pi r cubed. Another nice argument due to Feynman, or at least I learned about it from Feynman, I'm not sure it's his, to justify why gravity is a 1 over r squared force, is imagine every object is attracting every other object in the universe by exerting some kind of yankage. And you want to figure out how does the yankage vary as you get further and further away. So if I have a source, it's putting out constant yankage. So whatever this quantity yankage is, I put out a constant amount. The closer you are to me, the more you feel. Imagine you have a bunch of particles coming out of the center, and each one, when it hits you, says you go towards speed. The closer you are, the more particles will hit you. The further away you are, the fewer will hit you for a given size. If you then look at a sphere, no matter what the radius of the sphere is, the total yankage should be the same. And so since the sphere's surface area is going up like r squared, the effect of the gravity should be going down like 1 over r squared so that it balances and it will have a net constant yankage. So this is a nice geometric argument as to why gravity might be a 1 over r squared force. Okay, so again, a lot of really good stuff here. I'm not doing cylindrical coordinates. The only difference between cylindrical and polar is you just have z along the line. I see several of you have water bottles. If you're got hydrogen monoxide, if you don't have a water bottle, a lot of the desks have some kind of disinfectant, which is cylindrical in a large region. So cylindrical coordinates is not that different from spherical coordinates. And it's not that different from polar. It's kind of a mix between the two. Okay. Any other questions on the basics of spherical coordinates? So you love expressions like either the negative x squared plus y squared plus z squared. What would that function look like in spherical coordinates? What would x squared plus y squared plus z squared be in spherical coordinates? Yes. I'm taking e and I'm raising it to the negative x squared plus y squared plus z squared. So what is x squared plus y squared plus z squared in spherical? It would just be rho squared. This is the same as e to the negative rho squared. There's a couple of ways to see this. One way is we have the formulas for x, y, and z. We can calculate x squared, y squared, z squared, and add them. We'll have a lot of tricks. We'll have rho squared, rho squared, rho squared. Okay, everything has a rho squared. Okay, so I know x squared plus y squared plus z squared has to involve a rho squared. Rho squared times what? Well, I have sine squared phi, cosine squared theta, sine squared phi, sine squared theta. Oh, what's cosine squared plus sine squared? 1. So the x squared plus y squared is going to give us rho squared sine squared phi. We then add z, which is rho squared cosine squared phi. Sine squared phi plus cosine squared phi is still 1. So x squared plus y squared plus z squared is just going to be rho squared. How many times do you have to do this calculation in your life? Do we have to do this calculation ever again? No. Now that we've known it, whenever we see x squared plus y squared plus z squared, we can replace that. The other way of looking at it is here's the origin 0, 0, 0. Here's my point x, y, z in spherical coordinates. So I have a vector from 0, 0, 0 to x, y, z. What's the length of that vector? It's just the square root of the sum of the squares of the components. And that's right. So this is a nice consistency check that we're not doing anything absurd. Okay. So if I give you a function that depends only on x squared plus y squared plus z squared, you should be thinking spherical coordinates. What if it only depends on x squared plus y squared? Polar or cylindrical, something like that. And then if it has a terrible dependence, then you're out of luck. It turns out many problems only depend on your distance. So I guess there was a very brief moment where Kayla was in the video from 7 years ago. She is one of the few people in the world who can honestly say that the first calculus book they ever saw and worked with was an original version of Newton's Principia. So we actually have a copy at Williams. She was staying home that day from school with the children's center. And so in the old days, I used to actually bring students to the Rare Books Library because we have a phenomenal collection. And it's wonderful to see the actual books that changed the world. One of my favorite examples is a lot of people talk about Copernicus's work, but they don't actually quote from Copernicus's paper. They quote from a preliminary announcement, which has slightly different results in terms of the number of circles within circles that you need. And so it's another great example that people do not always look at the latest version. They do not always look at the final version. Earlier versions often get out, and that's what people talk about. It's a great way to tell what version someone was looking at. Have we talked about brown M&Ms in this class? So one of the members of the band Van Halen, Dave Roth, had in their contract that they must provide the band a bowl of M&Ms with all the browns removed. And failure to do this allows them to void the contract and keep all the money. Is this just rock stars being rock stars and just doing things for frivolous reasons? Anybody have any idea why they did this? Wonderful story. They had some extremely heavy equipment. If it was not set up properly, someone could be hurt. Did you set everything up correctly? Yes. Are you sure? Yes. Well, yeah. We set it up correctly. How can you quickly tell if somebody has actually read the contract and done everything correctly? Well, if they see a bowl of M&Ms with browns in it, they know people did not read the contract. And there was one time, I believe, where he very famously destroyed the room in a fit of rage. But it was a way to just quickly look in and see, have they read the thing? One place actually provided the bowl with nothing but brown M&Ms as a joke, saying, you got the con, you see what you're doing. But it's nice to be able to quickly glance at things and see what's going on. There's a tremendous impact of the search for understanding the motions of the planets and the development of calculus. One of the biggest problems was Newton trying to show that if you have a sphere of uniform density, you can assume all the masses in the center. And that's one of the most important integrals in the history of science, and we'll try to do that one later. All right, so the last thing to talk about is level sets. So is there anything people want me to talk about for level sets? So essentially what a level set is all the points that evaluate to the same value. So the level set of f of height c is all inputs that evaluate to c. So if you think of a beautiful mountain range, what is the level set? Let's say this is 0 here, 1,000, 2,000, 3,000. What points would be the level set of height 3,000? None. So you could say level set with C equals 3,000, and this is the empty set. So there would be no points that are 3,000 feet. What about C equals negative 1,000? What would that be? If you look at this picture. Are there any points where we're negative 1,000 feet? So that would also be empty. And if I wanted to look at 1,000, you'd say, oh, okay, this part over here is all 1,000, over here, a little bit over here, a little bit over here. And so if I look down on the x-axis, it would be this region in here, and then this region in here, this small little region over here, and then that region over there. So all points are the same height. When you look at the classroom that we live in right now, today, can somebody give me a good value for a level set for this classroom? Where you'll have lots of elements. Yes. 3 feet. Why 3 feet? Okay, so we're exactly 3 feet from the ground. I used to keep a tape measure on. Yes, okay. It is amazing how much stuff I keep in my backpack. All right. So I have a tape measure, a crappy one. So 3 feet is 36 inches. this can go up to 39, up to 3 feet. So I can't get too close, but it looks like 3 feet will get most of you where you're sitting. So I would have some cross sections of your upper bodies would be my level set. So 3 feet is a good value. There's a very natural value though for this graph where you have lots of things to level set. The ground. What else? Ceiling. What else? There's another really good one. Near the thoughts. You all have an example of this. The desk, right? All these desks should all be approximately the same height. And if you look at each point on the floor, and you see how high can you go up, and what's the highest thing you have in the room, for a lot of them, it will be these desks. And that will be your level set. So the question is, how do you find the level set? It is completely without calculus. So this is where you really need to know your algebra. And on exams, people frequently have trouble calculating the level sets. So let's say I give you the sine of x squared plus y squared. What can you tell me about where the values of sine of x squared plus y squared live? So what can you tell me about values of sine? Minus which one? So this is between minus 1 and 1. So the level set of height C is empty if the absolute value of C is greater than 1. Okay. What's the first value of C where we might actually have something? So do we all agree that if C is greater than 1 in absolute value, there is no choice of x and y, such as the sine of x squared plus y squared equals 6? So we need a value of C between negative 1 and 1. What do you think the first value is that we should investigate? C equals 0? No, I mean, there's many different ways you can do it. The way I'm looking at it is here's my y-axis, here's 1, here's negative 1, and I know the level sets are empty. Let's use the y-axis because I'm going to use x and y point of view. So I know things are empty between minus 1 and 1. I mean, above 1 and below minus 1. I know I have nothing in my level sets. So one thing is we could try, let's see what happens if we take 1. So find x and y such that the sine of x squared plus y squared equals 1. When we look at this, how does this depend on x and y? Should I be looking at this in xy space? Okay. You've got x squared plus y squared. When you see x squared plus y squared, what are you thinking? Polar. So in polar, this is the same as the sine of r squared equals 1. This means theta is free to do whatever the hell it wants. We need the sine of r squared to be 1. When is the sine of r squared equal to 1? So we need r squared equals, what's the first time sine takes on the value of 1? Pi over 2. When's the next time it's equal to 1? I'm sorry? Not 3 pi. 3 pi over 2 would give you negative 1. 5 pi over 2. what's next? 9 pi over 2. So the level set we would have R is the square root of pi halves, the square root of pi over 2, dot, dot, dot. It would be a bunch of circles. That would be the level set of size 1, the level set of height 1. I just look for all x and y such that my function evaluates to that choice of c. Could I do this for -1? Yeah. Instead of pi over 2, it would be now, I think you said earlier, 3 pi over 2. And in general, if I give you any number c here, it's the sine of r squared equals c. So then that means we would want r squared to be arc sine of c. Plus any multiple of 2 pi. We have to be a little bit careful, and that's why I wanted to do this problem, because unlike 1 and -1, unfortunately for other values, there could be more than one choice as we go around 2 pi that has the same value. If I look at, say, c equals root 2 over 2, what angle has a sine of root 2 over 2? Pi over 4. So if we want sine of r squared to be root 2 over 2, that's telling us we want r squared to be pi over 4. But there's another angle that works in addition to pi over 4. What else works? 3 over pi over 4. So it could be 3 pi over 4 as well. And then for each one of those, you would get to add any multiple of 2 pi. So this is how you do level sets. You just ask what are the possible inputs that will go to that. Okay. So this has no calculus in finding these level sets. It's just being comfortable with your algebra. And so go slowly and ask yourself which points will evaluate to that output. If I give you maybe f of x, y, z is x, what do you think those level sets are going to look like? I want all points that will evaluate to the same value. So first of all, is every C possible? Or will some C's have no X, Y, Z's that will give you that? I want to solve f of x, y, z equals c. So what would x equal, what would y equal, what would z? What would x do? My function is f of x, y, z equals x. I want f of x, y, z equals c. So what would x have to be? C. Are there any restrictions on y? No, y is completely free. What about z? Any restrictions on z? No. So the level set of height C is just going to be all points x, y, and z, such that x equals c. If you want c to be 5, it's just x equals 5. If you want c equals 9, it's x equals 9. So what kind of object is this? 1x plus 0y plus 0z equals c. What is this the equation of? Yeah, vertical plane. So this is just a plane. Okay, this is, n dotted with x, y, z equals n dotted with r is the plane. This is the equation of a plane. I just happen to have two of the coefficients being 0 to try to fool you. But I have two free parameters. This is going to just be a plane. So this is something that only depends on my x displacement. So an example, rather than using x, if I use z, maybe we might be talking about the temperature of a pool or an ocean, and maybe all that matters is how high up you are. Or we might be talking about some kind of concentration of something that's being dissolved, and all that matters is just how high up are you. All right, so this is a good place to stop. I will send you details about when the first exam will be. And then, as always, if you have questions, let me know. Your review sessions,